Sure. I'll start sharing my lecture slides. So the most important thing I want to go through today is quantum critical points and non-Fermi liquids, because that's the case where correlated electron systems are really driven to the brink of correlations being so large that all our theoretical descriptions that we have at hand and that we've looked at actually are stretched to breaking point. So before I assume that, am I correct to assume that nobody has heard about quantum critical points yet? Hands up if you have.
Hands up if you have. Hands up.
Okay, so Paul has heard of about quantum critical points, but it looks like everybody hasn't. So what I'll start with is to walk you through classical phase transitions before we make our way to quantum critical points, which are a quantum phase transition. Okay, so classical phase transitions. Let's have a look at the characteristics of classical phase transitions first. Are you all confident with first and second order classical phase transitions? Okay, so you've heard about it, but let me just walk you through through the main differences and their bearing on quantum phase transitions. The distinction is between either first and second order, or what's actually more important for our case is whether it's discontinuous or continuous. And discontinuous means that one of the first derivatives of a thermodynamic potential has got a discontinuity, whereas second order or continuous means that the first derivative is continuous and only second derivatives may display a discontinuity. Technically, one can also define third order and higher order phase transitions, but for the sake of what we're going to go through today, they are continuous in their first derivative, and hence all the same methodologically is going to apply. And the continuous versus discontinuous transition does manifest, of course, that there's a latent heat associated with a first order phase transition, whereas there's no latent heat in a second order. Right at the phase transitions, in a first order phase transition, the two states that are bordering that transition are different. Whereas right at the second order phase transitions, the two states bordering the transition are actually identical. Now that I hope that's not too confusing, but let me illustrate that on the next slide, because you can, for instance, come to the conclusion. So different states you know very well. You know, water and ice, liquid water and ice are clearly different by symmetry, in fact. And hence it is a first order transition. So symmetry breaking always dictates, no, actually symmetry breaking, that means that there is a phase transition. It doesn't mean whether it's discontinuous or continuous, but there is also a discontinuity in the ice water liquid solid transition in the specific heat and in the volume. Second order phase transitions are not so common in daily life, but actually once you study physics, you'll come across those in many cases. And I'll look at the ferromagnetic second order phase transition with you in a minute, which you might have seen also in the magnetism superconductivity courses, where you've probably derived that this is second order at the Curie temperature, and the magnetization starts to rise as it's sketched here. The magnetization is the order parameter, starts to rise continuously. That means right at the transition, the magnetization is actually zero in the disordered phase, so above the transition temperature, and it's zero in the ordered phase because that ordered phase just starts to emerge here. The minute you go only a small amount below the transition temperature, of course, the magnetization starts to rise to a finite value. But the zero magnetization is still a solution of the ordered state right at the transition temperature. That means the states are really identical, and it's only energetic. We can, of course, we'll look at the energy gain from the ordered state in a minute. And volume and entropy, being first derivatives, of course, have to be continuous and hence be the same right at Tc for the ordered and disordered state. Okay, as promised, let's look at some sketches of what a ferromagnet looks like. So one can run simulations like sketched here on the left. These what looks like war of ants is a simulation where black plaquette, the nodes say spin up, white plaquette spin down, or actually more classical magnetization up, magnetization down in some small domain. And it's maybe a 2-hour exercise to program such a simulation in Python. What you can do is, for instance, assume that there will be some interaction with the neighboring plaquettes, flipping it in the same direction like the neighboring plaquettes with a certain probability. And then you can also include some randomness, flipping it in a random direction with a Boltzmann factor kbt e to the a probability e to the minus kbt over t. So that's what I've done here, and what you can see is that higher temperature means smaller patches of same orientation. Lower temperatures means that these patches grow. In addition, here at high temperatures, the average of white and black is actually same. So there is no net magnetization to the material. Whereas you can see here, there's a bit of a tendency for the white to become larger. And actually, that's maybe a bit confusing because in the end, at lowest temperatures here, it's the black that really wins. So that's the type of fluctuations that can happen, in particular in finite size systems, as we see it here. So you can already again see that the disordered state and the ordered state are really the same in terms of their behavior right at the transition temperature, because you've got net 50% black and white here at high temperatures, and then the ordered state with 50 plus delta or epsilon % of the winning color is just emerging out of that even average right at the transition temperature, and only wins a large majority at lower temperatures in these simulations. Okay, so what does this mean, and what's the characteristics of classical phase transitions? The characteristics are that, as I've already mentioned, that the patches of the same magnetization, or in this case, same color here, start to grow. And what that means is that the physics is going to be averaging out over larger and larger patches. And it will be larger and larger patches actually fluctuating from one orientation to the other. So you could have a patch as big as this, flip its entire color at close to the transition temperature, because it costs very little energy to do so, as the two states are energetically quite close. Whereas here, for a large region of black to flip to white would cost much more, because you're at higher temperature, you're further away from the energy being equivalent. So larger fluctuations means that we are, on the other hand, averaging out the physics over a larger and larger region in space. And what that means is that the underlying microscopic details will actually be not important at all close to the phase transition, because we have such large range, large patches that fluctuate from one orientation to the other. And that's what makes classical phase transitions really classical, in the sense that even if a ferromagnet has, of course, some underlying quantum mechanics which give rise to the exchange interaction, for instance, that couples the neighboring spins. But that's not important at all as you come very close to the phase transition. It is the large patches fluctuating from one to the other magnetization that dominate the physics, and they're entirely described by classical physics. I mentioned Boltzmann statistics that you apply here, and hence that really makes a phase transition classical. I've sketched here what is expected, for instance, for the correlation time. So that's if you look at one spot, how likely is it for it to remain of the same orientation for a given time. That correlation time does diverge at the transition temperature. So for ferromagnet Curie temperature, in the same way, or not in the same way, but it does diverge just as the correlation length diverges, which is a measure of the size of these patches. They actually diverge both with some exponents, and these exponents are, of course, universality classes, class specific. There's a different exponent for the correlation time and for the correlation length, but that's a bit more details. The most important message to take away is that quantum mechanics is averaged out over these patches, and hence everything is described by classical physics in the sense of Boltzmann statistics. Okay, everybody familiar or happy with this recap before I go to the quantum phase transitions, or are there any questions about classical phase transitions?
Not a question about classical phase transitions, but I've heard of quantum fluctuations like this, but I'm not quite sure what it really means.
I'll come to that when we get to
the quantum ones, yeah. Okay,
when we get to quantum phase transitions. Okay, so let's now look at what happens if. So I've made the case that this transition temperature is a finite temperature where we've got, of course, fluctuations of the order of kBTC happening, and that's what allows to switch even large patches. Now, what happens if we suppress that transition temperature to closer and closer temperatures? So this left axis of this temperature tuning parameter phase diagram corresponds to what we've been considering on the previous slide, namely the finite temperature, transition temperature here. And I've made the case that there will be a range around this where everything is purely classical because the correlation lengths and correlation time average out any microscopic details. Now, kBTC becomes, so let's now assume that there is a tuning parameter that could be changing the spacing of the atoms. You could, in an experiment that can be realized by applying pressure. But there's many more possibilities like magnetic fields, strain, electric field, and quite a few other things. So let's just say that there are tuning parameters that can reduce transition temperatures. And I'm here talking about second order phase transitions. Actually, on the previous slide, I was also talking about second order strictly, because otherwise there would be a finite energy between the two states, and all of what I've said would not apply. Okay, so tuning down that phase transition means that the range that is classical around it must also become smaller, because kBT or kBTC, the thermal energy that's available right at the transition, becomes smaller, and hence there's less energy available for large patches to fluctuate between the two states. And eventually, once transition temperature is suppressed right to zero temperature, of course, kBTC is also zero, and hence there is actually no thermal fluctuations happening anymore. Okay, so that already is an indication that classical physics will stop when we reach when we suppress the transition temperature all the way to zero. And we will see that this indeed means that quantum fluctuations are going to be important there. And that's why this is called a quantum critical point. The finite temperature transition transition here or there is often called the critical point. Here it looks like a line, but if you just intersect it down cooling and temperature, then of course it appears as a point. And a quantum critical point is essentially, the extension of that to zero temperature, where quantum fluctuations become important. So how can we see that quantum fluctuations are important here? Now, let's consider we are in the ordered state here. And on my previous slide, I've had the sketch of the material being essentially all magnetized in one direction, or in the sketch, it looked as the material was black everywhere. If we start there, it's perfectly black. At zero temperature in that simulation, it would indeed be completely black. If we now approach the quantum critical point, there is no thermal fluctuations. So hence there's nothing which will actually flip small or large patches to the other color and to the other magnetization orientation. And hence, even if you go beyond here in terms of thermal fluctuations, nothing would actually destroy the ordered state, or in other words, melt the order. And you would actually left with a puzzle. How is the material actually going to convert from perfectly ordered to completely disordered if there's no thermal fluctuations available? However, there is, of course, quantum fluctuations present, and they will take over this job. Because if you're on this side of the quantum critical point, you're in the regime where it's energetically favorable to form the ordered state. So say a ferromagnet. On this side, on the other hand, it will be energetically favorable to form the disordered state. So a paramagnet in this example. Right at this transition, because this is a continuous phase transition, the energy of the two states must be equal. That means the difference in energy between those two states will become zero right at the quantum critical point. Zero energy difference, of course, means that it is now it costs nothing. It costs essentially nothing for quantum fluctuations to occur, and that could be again patches of one to flip to the opposing orientation, and we will have patches of different size and also fluctuating in time, and they can just flip from one state to the other state locally, and that means on average we can then again get back to the completely disordered state on the right hand side. These patches cost no energy right at the quantum critical point because there is no energy difference between the ordered and disordered states. This also means, because there is no energy cost, means that there's also no energy uncertainty, and by Heisenberg's uncertainty principle, that means that there will be the largest uncertainty in their lifetime, and hence you will have these fluctuations being long-lived. In fact, the correlation time diverging right at the quantum critical point. So the answer to the paradoxon that I was getting to from the classical point of view is actually solved by the fact that there can be patches that fluctuate simply because of Heisenberg's uncertainty principle, in that the energy and time are limited in how well they are defined, because that means also here where the energy is maybe still a little bit on the ordered side, that means we've got a delta E which corresponds to the difference in energy between the ordered and disordered state. That means that there is a finite time over which fluctuations can exist to the opposing state, and hence we will also get a divergence of fluctuation of correlation time as we approach the quantum critical point right at zero temperature. We shall see that there's slightly different exponents that govern the quantum critical behavior, but the fundamentals are analog to some extent. Okay, now I've been talking about zero temperature a lot. You might say that won't matter ever in real life, because in no experiment we will reach zero temperature. That's of course true. However, we can also see quite some influence of this quantum critical point to finite temperatures. And that requires us to consider the combination of thermal fluctuations and quantum fluctuations. Quantum fluctuations are characterized by the energy it costs to flip between the two states locally, and that's what I've here denoted as h bar omega, or h bar omega c, because it's the critical part of it. And of course, thermal fluctuations are associated with the energy scale, the Boltzmann energy scale, KBT. As long as we are in the ordered state, the energy between the ordered and disordered state is always larger than the thermal energy. Otherwise, it would not be ordered. That prevents it essentially from being destroyed by thermal fluctuations. On the other hand, and the same is true essentially in the disordered state, because here the energy balance is, of course, in favor of the disordered state. But again, the energy difference between the two states is going to be larger than the thermal energy. And that's why we firmly stay within the disordered state. However, I've made the case that right at the quantum critical point, the energy difference between the two states is 0. Right at the quantum critical point, the thermal energy is also 0. But if we now go up in temperature here, we're still at the same value of the tuning parameter, and that's what's going to decide in the Hamiltonian which of the quantum states is lower in energy. As we're still at the same tuning value, the difference in energy between the quantum ordered and disordered state is still 0. And yet we here have a finite thermal fluctuations present. So that that means we now enter a regime where, from a quantum point of view, the material is still critical, but nevertheless we are at finite temperatures. That means quantum fluctuations between the ordered and disordered state can occur in this regime, and on top of that, thermal fluctuations can occur. This is actually not just a line, because that same argument holds as we go slightly to the right. Yes, here the balance in terms of energy is technically favorable for quantum disordered. However, it's only a little bit favored in that direction, and there's given that the temperature is finite, thermal fluctuations are finite. Hence, we can go some distance to the right, where the thermal fluctuations are still going to be larger than the energy difference between the ordered and disordered state. And the same holds if we go to the left here. And that's the reason why we've got this fan of a region where quantum fluctuations between the ordered and disordered state are present, and thermal fluctuations are present too. So they can both work there. Everybody still with me? And I understand that this is a reasonably challenging concept. Don't see any objections. So let me carry on what that means. So thermal fluctuations present means that we're averaging out over some spatial regime, time regime. And in fact, it means that if the state is sitting up here or here, or here, the thermal fluctuations are averaging out and are larger than the quantum fluctuations, which actually means that the system cannot know where it really will end up if you cool down. So if you're sitting right here, thermal fluctuations are larger, and hence they mask completely, they mask whether the quantum fluctuations point towards the quantum ordered or disordered states. In other words, cooling down the system here, it will not know whether it's going to be ordered or disordered. It will only know once it crosses this line into the classical regime and into the ordered state. And in other words, that means the state up here is essentially, yeah, it's not a thermodynamic state in that sense with sharp phase boundaries, but it is a crossover regime where the physics is really dominated by these quantum fluctuations. Okay, I made the case that these quantum fluctuations have divergencies like the classical phase transitions, and that governs most of the physics of what happens at lower dimension, at lower temperature, in this quantum critical regime. Now, I'm not going to go into all of the detail, but what I would like you to take away is that one can now write down a theory of this quantum critical behavior, which is a further development of the behavior at classical phase transitions. So at classical phase transitions, the renormalization group behavior is what gave very good insight into what's happening there, and also describes all these exponents and universality classes. One can extend this for quantum critical behavior. What is happening in addition in quantum critical behaviors is that essentially you've got an imaginary time in the wave function, in the Schrödinger equation, that, however, acts as if it is contributing to the effective dimensionality of the system. Because on a classical phase transition, you have fluctuations happening in whatever dimensionality, and that is important because that actually bears great relevance on what universality class you're going to end up in. In the quantum critical regime, you will have fluctuations occurring still in time and space, but the temporal fluctuations of, if you write them down in quantum theory, act as if they contribute another dimension. And that's why one can describe the quantum critical behavior with an effective dimension. That's the actual dimension of the system. Could be three-dimensional for something like iron. It could be two-dimensional for something like graphene. Plus Z, where Z is actually the exponent of the temporal fluctuations. I had it already up here as an exponent on how the ordering temperature occurs. I've also had it here in the divergence of the correlation time for the classical fluctuations. So this exponent Z describes essentially how does the divergence of the correlation time differ from the divergence of the correlation length. Don't worry about the details. The important bit maybe to take away is that the effective dimensionality that can describe a quantum critical behavior is given by the spatial dimension plus this this dynamic critical exponent Z. Now, if one thing that is clear from the renormalization theory of classical phase transitions is that there are so-called critical dimensions, so behavior in which is actually the four-dimensional system. So anything that comes above 4 will behave quite different. Will be well described by renormalization group theory, and adding this exponent Z often brings you actually into that regime. So what's the result of that? Without going into more detail of that theory, the result in terms of experiments is that there's plenty of predictions of how certain properties should behave at certain quantum critical points. For an overview of this, you can actually look at the reference that I've listed here on the first slide. This review of Hilbert von Leuenhuizen. Very good reference for all of that. You'll in particular find also this table there. So if you look for material which is characterized by a certain dimensionality, say 3 dimensions, and a certain dynamically critical exponent Z. So that's, for instance, for an antiferromagnet, Z is 2. For ferromagnet, Z is 3. That means that you'll get now certain specific behavior in the temperature dependence of certain quantities. So for instance, in the specific heat, which is here plotted as C/T, in a normal metal, you remember we expect that the electronic contribution will be constant, namely gamma. At such a quantum critical point for an antiferromagnet, you expect that there will be a correction of minus A times square root T. So quite some different behavior. Still reasonably analytic, and actually it will go to 0 as you go to 0 temperature. In 2 dimensions, actually it looks already different. Here you can see that you'll get a critical contribution which is log T0 over T. For the limit of 0 temperature, this will actually diverge. So the specific heat will have a divergent contribution at an antiferromagnetic quantum critical point in a two-dimensional or quasi-two-dimensional material. And I'll show you examples on some of the upcoming slides that this is indeed observed. And you can, of course, look your way through this table to check for some other properties. Down here, the table I've got is actually both in terms of temperature and R, the distance to the quantum critical point. So you see R is here the tuning axis, and 0 corresponds to the quantum critical point. So that does not only tell you what the specific heat will be doing as a function of temperature in this regime, but it also tells you what the specific heat will be doing as you tune here to the right or left in this quantum critical regime. Okay, one can of course look at quite some more examples, but that is quite specific, and I don't want to work through that with you in more detail now. One more quite remarkable and smoking gun experiments that I'd like to highlight is actually is more important in some extent than these divergencies in the specific heat, because they could technically, divergency in the specific heat could have different origins. It could have origins like magnetic frustration. The electrical resistance rho here, we also see that this can have quite some remarkable different temperature dependence compared to Fermi liquid behavior. Again, that can have different origins. For instance, the T linear that we see here in the antiferromagnetic two-dimensional case is of course something which we also observe at room temperature due to phonons, and all it takes to extend that to lower temperatures would be to lower the Debye temperature to 0 temperature, which actually is also a way to look at certain quantum phase transitions. Okay, so I was promising some more smoking gun experiments, and one smoking gun experiment is the so-called Grüneisen ratio. The Grüneisen ratio is defined as the ratio of the thermal expansion, often described by beta, divided by the specific heat, C here. They're both derivatives of the entropy, namely with respect to pressure and with respect to temperature. That means you can now use Maxwell relations to convert that into the derivative of the energy with respect to pressure, and that means at a pressure or volume-driven quantum critical point, you expect that there will be a 1 over energy, where energy is the energy scale of the problem, namely the difference in energy between the ordered and disordered state. And this, we've already made the point that this energy between the ordered and disordered state is going to go to 0, and hence we expect that this whole expression is going to diverge, because this needs to evolve in a smooth fashion at a continuous phase transition. So that means that the Grüneisen ratio is expected to diverge, and we've used entirely thermodynamic arguments here. So that makes this quite a robust argument, robust against things like the details like the upper critical dimensions, and so that I've mentioned for the renormalization theory. So hence one can argue that a divergent Grüneisen ratio is really a very solid evidence for a quantum critical point to happen. And on the right hand here, I've got some data that actually illustrates this. So in the inset is just the plot of this Grüneisen ratio versus temperature. Looks like a quite steep function. And a better way to show that it is indeed divergent is to use a double logarithmic plot, because now we can see that this is indeed as following a straight line over a temperature range of more than 1 decade. And a straight line in a double logarithmic plot, of course, means some power law behavior. With this straight line pointing up, it means actually it's a divergence of something like t to the minus something. In this case, it's actually -1. Okay, so a divergence in the Grüneisen ratio is one of the best pieces of evidence that one can collect for a quantum critical point. All right, so I hope I've presented to you the concept of quantum critical points, quantum fluctuations, and what their influence is on the properties of materials. And certainly such a divergent Green-Eisen ratio, you would not expect that at all in the Fermi liquid theory. Next, what I'd like to do is actually to link this to the topic of last lecture, namely heavy fermions. Heavy fermions turn out to be an excellent playground for studying quantum criticality. And indeed, this cerium nickel 2 germanium 2 shown here is such a heavy fermion. Cerium is the one contributing the local moments. Nickel and germanium, if you wish, you can regard as the vegetables contributing the conduction electrons. And one has again happening the Kondo effect here and the Kondo lattice effect. And this is quite a nice heavy fermion metal. So why are heavy fermions good for quantum criticality? The answer is that they can be tuned very easily. I've made the case last time that having the ingredients of local moments and conduction electrons, we will have a Kondo effect taking place. And I've made the point that there is heavy quasi-particles that can emerge. I've also indicated that the conduction electrons will end up screening the local moments, and you can picture this as the local moment essentially, being surrounded by a cloud of conduction electrons of the opposite spin. It's of course not a static picture. I made the point that there's scattering happening all the time, Kondo scattering, which can lead to the spin of the conduction electron and local moment flip. And hence, on average, the local moment will actually be flipping up and down all the time. And on average, that means it's going to be 0, and that makes it paramagnetic. And of course, it is a Fermi liquid state that I made the case. I've also talked to you about the overscreening to lead to effects like the Friedel oscillations in the charge density, or to the magnetic interactions due to the so-called RKKY interaction. So any magnetic interaction, so I made the point that a local moment here placed in this coordinate in this sketch at coordinate 0 will have conduction electrons attempting to screen the local moment, but it won't manage over a certain distance. So in that range, a second local moment would orient parallel. It will then overscreen because of the sharp cutoff at the Fermi level, meaning that if you had a second local moment at this distance, it would couple antiferromagnetically. And an initial overscreening, of course, has immediately the consequence of further overscreenings, and hence these oscillations, such that you can have, again, ferromagnetic, antiferromagnetic, and so on. Fundamentally, you can describe such a magnetic ordering as a Hamiltonian, which will have dot product of two local moments with some interaction strength that will depend on the distance in this case. The important bit is that it can lead to a magnetic ground state. So both these interactions, Kondo effect and RKKY interactions, stem from the same ingredients, namely local moments in a sea of conduction electrons. So we can expect that both will actually be present in heavy fermion materials. Yet they lead to completely opposite and incompatible states, namely a paramagnetic state on the side of the Kondo effect and a magnetic state on the side of the RKKY interaction. And hence, depending on which of the two wins, we will get a different ground state at 0 temperature. And that's exactly where the tunability of heavy fermions stems from, because all we need to do is see which one of these depends on some external tuning parameter in a specific way and compare that. What turns out is that both indeed depend on the exchange interaction between the conduction and F electrons, which but in a slightly different way. The Kondo effect depends on the exchange interaction J in an exponential fashion, the RKKY interaction in a square fashion. The square is always going to dominate at weak coupling, small J values. Exponential will eventually take over at large coupling, large J values. And hence there will be a crossing somewhere where the two will be of equal energy, and hence they are essentially in competition without a winner. Now, RKKY, I made the point, will lead to magnetic ordered state, and in most materials, indeed, it's found that it leads to an antiferromagnetic state. So that's probably down to the typical distance of local moments in these materials. But as we tune to a larger value of J via some tuning parameter, which could again be pressure, this antiferromagnetic transition temperature will be suppressed because the energy difference compared to the Kondo state is going down. And eventually the Kondo state is going to win. And what I've sketched here is the Fermi liquid temperature is actually not an ordering temperature, but that's the regime below which these quasi-particles are well described by Fermi liquid theory. They will be heavily renormalized because all these fluctuations emerging from that quantum critical point, they couple to these quantum quasi-particles and make them heavier if you're closer to the quantum critical point. So how can this be observed now in experiments? Let me show you some examples. This is an example of cerium copper 6 doped with gold, where some of the copper is essentially replaced with gold. This diagram shows the evolution of the ordering temperature. So it's antiferromagnetic below and paramagnetic above. Very importantly, you see that the ordering temperature here is 0 at a gold concentration of 0.1. So that means we expect a quantum critical point at 0.1 X or 10% gold. And right at that quantum critical point, we can now look at what are the experimental signatures. So 0.1 on this graph down here of the specific heat is this black dots, and they are actually inside this bunch of curves, which all show a straight line behavior here on this semi-logarithmic plot, which means that the specific heat is indeed diverging as log 1/T. If we go slightly to the left or right, so let's look at what happens if we go towards the paramagnetic case. That's here 0x. That will be the triangles pointing towards the left. You can see that here. It starts out similar because at high temperatures, it won't know. You're essentially in that quantum critical fan, which emerges from this quantum critical point. But at low temperatures, you get in the Fermi liquid state, and hence this starts to turn over and level off. And you can read off now essentially a constant, virtually constant specific heat coefficient, C/T, that's equal to the gamma coefficient, which here is of the order of 2 joule per mole Kelvin squared. So enormous compared to normal metals. We've had the case in the first lecture, potassium has 2 millijoule per mole Kelvin squared. Again, the hallmark of the heavy fermion behavior, but also of the proximity to the quantum critical point. If we go on the ordered side, so say 0.2, so that would be here, then we've got an ordering temperature of something like 200 millikelvin. And indeed, we can see this in this graph. So here, the specific heat has this steep rise, which corresponds to the magnetic ordering. And then it again saturates at least much better than this divergence that's here present at 0.1 gold concentration. And that signifies that, again, we enter some quasi-particle description, again, with very heavy quasi-particles. Okay, what's another example of this heavy fermion behavior? Another very prominent material is terbium rhodium 2 silicon 2. Here it's the terbium, which makes it a heavy fermion, rhodium and silicon contributing conduction electrons. Here I've plotted the susceptibility. And again, we can see that there is some divergence happening. And it's happening very close to where the ordering temperature is suppressed. So the ordering is visible here as a kink, and you can see it becomes constant below that transition temperature. If we apply a magnetic field, so this is an antiferromagnet, we will suppress the ordering temperature. So you can see that here this kink shifts to lower and lower temperatures. And for a field above, so this curve corresponds to 40 millitesla. For a field of 50 millitesla, it looks like it keeps on diverging to lowest temperatures. So that's again one of the hallmarks of quantum criticality. And then when we go beyond this, you can see it goes over maximum and starts to saturate quite clearly in this bottom curve. And you can see that it saturates at lower values the further we go away from that critical field. Again, that signifies, because this constant value here is the so-called Pauli susceptibility. It's a measure of which is constant is proportional to the density of states. So it signifies that the density of states is dropping or the effective mass is dropping. We're getting towards less heavy quasiparticles. Ytterbium rhodium 2 silicon 2 also shows this divergence of the specific heat. So this is again one such semi-logarithmic plot. In zero field, it actually even diverges faster than the log T, which is still an open question why it does that. That's also actually not just true in zero field, that's also true in finite field. And ytterbium rhodium 2 silicon 2 also shows non-Fermi liquid behavior in the resistance. What we expect in Fermi liquid theory is that the resistance follows a T-square behavior. In this color plot, that corresponds to an exponent of 2. And indeed, we can see that here on the right-hand side, where we are deep in the Fermi liquid paramagnetic regime. We can also see it inside the antiferromagnetic state down here on the left side. But in between, where the antiferromagnetism is suppressed to zero temperature, so that's where the quantum critical point lies, we can see that there is this non-Fermi liquid behavior all the way to lowest temperatures. And we can also see this fan of quantum critical behavior spreading out above this quantum critical point. So very beautiful example of this quantum critical behavior. This regime is the Fermi liquid behavior. If we sit inside that Fermi liquid behavior and get closer to the quantum critical point, we still see the material still feels the effect of becoming more, getting closer to that. And one way that is observed is, for instance, I've got here measurements which I've done during my PhD thesis. So if we measure the resistance inside this regime, we can measure the temperature dependence by measuring resistance versus temperature down here, and it follows very nicely T-squared. That's visible here, for instance, by this blue color code. And one can extract the coefficient of that T-squared behavior, so-called A coefficient, and that's plotted down here. And it's found to diverge as we get closer and closer to the quantum critical point. Again, the A coefficient being proportional to the density of states tells us that the effective mass is diverging as we get closer to the quantum critical point. And what that one simple way to understand this is that the correlations become larger because larger and larger regions can fluctuate, quantum fluctuate between the ordered and disordered state. Right, so I'll actually skip the next slide, which essentially shows that there is theory. Yeah, okay, I'll just make a brief note on the next slide, namely that so far I've started by showing that huge table with all the predictions for the different exponents of the different properties. That theory, as I mentioned, is based entirely on is essentially an extension of the classical critical theory, and hence it's based entirely on the notion of an order parameter, which then induces fluctuations. However, there are some experiments which indicate that that it is required to consider theories beyond order parameter, and that manifests, for instance, in the violation of the Friedemann-Franz law in specific materials. It also manifests in the in certain scaling properties at different quantum critical points. So that's measurements, in fact, which I have also done in my PhD thesis. But I think I'll not go into much more detail here in order not to confuse you too much about quantum criticality. Okay, I'll also skip over this slide, or briefly go over it only. Magnesium silicon and magnesium silicide and zirconium zinc 2 are materials which do show non-Fermi liquid behavior, most significantly a resistance that follows T⁵, not just in a fan like we've discussed before, but actually in an extended regime. That clearly is some correlated behavior going on. It's not quite clear why it is an extended regime and not just a fan. It's one example where things point towards some further physics to be made. Okay, one important thing I would like to add to quantum critical behavior before we finish is that often new states emerge at quantum critical points. And schematically, I've sketched that here on the right, that upon suppressing a classical phase transition, what is observed very regularly is that a new state like superconductivity takes over before the quantum critical point is actually reached. The most famous example is cerium palladium to silicon 2, which is these results. So the phase diagram looks like this. It orders antiferromagnetically at 10 Kelvin at ambient pressure, with pressure that transition temperature can be suppressed exactly as expected with that competition between Kondo and RKKY interaction. And you can see that there's clear non-Fermi liquid behavior because the resistance follows a T⁵ behavior here. But then actually the resistance drops to 0, marking the onset of superconductivity. And that superconductivity exists in a small dome just around that avoided quantum critical point. It's avoided because that magnetic transition doesn't exist anymore inside the superconducting state. There's further examples, cerium copper 2 silicon 2 that I mentioned as the first heavy fermion superconductor. Indeed also shows such superconducting domes, a bit more complicated though, because here we've got antiferromagnetic order with a superconducting dome. And we've also got what's called a valence order with a critical point and a second dome around that. So actually a double example of producing new states at quantum critical points. There's even further examples of a ferromagnet, here in this case uranium germanium 2, which has superconductivity inside a ferromagnetic state. So this marks the ordering temperature of the ferromagnet. And then there's a superconducting dome inside. In fact, what I have not shown on here is that there's some evidence that there's actually another ordering temperature in there, which becomes critical right here. Okay. So we can essentially establish, and yet there's yet more examples like the cuprate superconductors, which do show superconductivity outside the ordered phase. So we would not associate that with the quantum critical behavior, but I'd like to add this, and I'll come back to the cuprates in more detail on one of the subsequent slides. But most importantly, we can notice that it is a common concept in physics that there's new states emerging at quantum critical points. And for cuprates, that's actually heavily or quite consistently discussed whether that's actually also the case thanks to a quantum critical point that lies at higher doping. So X here marks the level of oxygen doping. And schematically, that can be summarized like this, that cuprates have an antiferromagnetic phase at 0 doping. Then they've got something which is called the pseudo gap. It's still debated whether that's a thermodynamic phase, and hence it's still debated whether they can actually become quantum critical. But the superconducting dome is centered roughly around where that would become quantum critical. And hence, there is a lot of research going on that tries to figure out whether there's a relation. And that's certainly ongoing, and I wouldn't be, I would suggest, I would not be brave enough to say it's one way or the other. The cuprates indeed observe or show also quite some pronounced non-Fermi liquid behavior. For instance, the resistance here, as you can see here, is linear over a huge temperature range, actually from 1000 Kelvin all the way to the transition temperature. So that's clearly inconsistent with the T squared that you expect in Fermi liquid, also the T to the 5 that you expect at low temperatures due to phonons. There's also further evidence that the electron masses actually do diverge at certain points in the cuprates. So this has been measured with quantum oscillation experiments, which show this divergence of the effective masses, the inverse effective masses pointing towards the exact location in the phase diagram where it does diverge. That points actually to there's several potential phases or places where it can diverge, or where there's evidence for it diverging. For instance, here it looks like it's diverging right there, and one can see that this might actually hint towards one dome of superconductivity, and there is an observed dip in the transition temperature, which could be because it's a combination with a second dome of superconductivity. Again, this is ongoing research, and there's quite some debate going on what's really happening in the cuprates, and solving that would make a big contribution to the field, to condensed matter in total, and could help to find better superconductors at higher temperature. Okay, maybe I'll just briefly mention that for cuprates, of course, there is the idea that the pairing is unconventional in the sense that the Cooper pairs consist not of singlet states with spin up and spin down, but of triplets. No, actually in cuprates, the idea is still that they are singlet, but not with a zero momentum L equals 0, which would correspond to the S wave case, but with a momentum L equals 2, which corresponds to what's called the D wave case, in analogy to the orbital description or the spherical harmonics. And the gap would look roughly like this around the Fermi surface. This is much more consistent with antiferromagnetic coupling between the electrons in a Cooper pair. And that actually makes sense if we consider that we're close to this antiferromagnetically ordered state. And again, it highlights that there might be some relevance of quantum criticality there. The consequences, or the fact that this gap indeed has these nodes here where it is 0 and changes sign, has been observed with several experiments. One is includes the ARPAS measurements, which here show the gap as a function of angle at different temperatures, and quite clearly show that there's a change in the gap's magnitude. Lots of research going on, which I don't want to go into too much detail right here, because that could be a full lecture series by itself. The final thing that I'd like to mention is actually some recent connections that have been made between quantum critical points and work in the so-called Andy de Sitter's conformal field theory. This theory has been developed to describe strings, and has in fact its applications in describing black holes. Funnily enough, this can be mapped with some holographic projections on solid state problems. And there's first predictions coming out of this, what that means for the behavior of quantum criticality. I don't want to give any exhaustive description of this theory. Again, that would be a lecture series in itself. But it's a promising route that one can solve this very difficult many-body problem that is not so easy to describe with renormalization theory. And the only other contender to be a good description of the material is what's called the dynamical mean field theory, which actually allows to run computations of materials like cuprates and quantum critical materials, but very quickly encounters the expense, the computational expense of many body problems, and hence has got its limitations. Okay, so with that, I'll finish for today. And the main message that I hope you take away is that quantum critical points are phase transitions at zero temperature, which nevertheless influence the behavior of materials at finer temperatures, because we've got the thermal and quantum fluctuations working in concert there. Okay, I'm happy to take any questions about this, if there are any.
Hi. Yeah, thanks for the lecture. I'm just still a bit uncertain about the concept of quantum fluctuations. Is this something that can only really be understood in terms of quantum field theory? I'm wondering if that's my issue, because I don't really have a background in quantum field theory.
It is, of course, very well possible to write it down in quantum field theory and second quantization with creation and annihilation operators. But I've deliberately avoided writing down too many Hamiltonians today. You can understand it equally well in this picture of white and black patches of the magnet, which fluctuate between ordered and disordered. So if I flip back to those slides, this picture of patches fluctuating as a function of temperature is similarly valid as you approach a quantum critical point, because you'll have quantum fluctuations between the two states, and they again will be larger patches as you get closer to the quantum critical point. Does that kind of answer your question?
Well, I mean, I kind of get the idea. It's just I don't really have a good understanding or picture of what these quantum fluctuations actually are. I'm kind of picturing, like, you know, some kind of pure state that's evolving in time. And with thermal fluctuation, I have this idea of the system is interacting with, like, you know, the outside universe. So there's this thermal fluctuations, kind of random changes going on. But I'm thinking of a quantum system like as a closed system at zero temperature, so that you should have just a pure state evolving in time. And I'm not really sure
I think we should probably consider both this thermal case and the quantum case to be closed systems. The only interaction that happens is with the external temperature being set. So meaning that there's entropy that comes in or gets out. In the same way, the quantum system is also not completely closed, in that we need to tune it somehow. So that means we could, for instance, use pressure to change the lattice spacing in a real material. And then, if you do that, you can end up with a very similar picture in these black and white sketches here. That you've got patches of. Consider each of those spots to be an atom, which could be a serum atom in a heavy fermion. And black means magnetization pointing up, white means magnetization pointing down. That's two quantum states. And they will have they will fluctuate due to temperature at finite temperatures, but they will equally fluctuate at the quantum critical point, because the energy difference between the two states is zero.
Because the energy difference between the two states is zero.
Okay, so is it a valid picture to have in mind that you have some quantum sort of ground state, and then you vary some parameter like the pressure, and so your system is no longer in the ground state, so there should be some kind of excitations? Is this the kind of...
It will always be in the ground state if we just go along this zero temperature axis. The ground state, however, changes, because the ground state here will be paramagnetically ordered, because that's lower in energy, whereas here the ground state is paramagnetic, meaning it's not ordered. On average, the magnetization is zero, because there's equal atoms that have positive and negative magnetization. So we always stay in the ground state at zero temperature. But the two ground states that you've got on the two sides are of equal energy when you're right at the quantum critical point. And that means it costs zero energy to fluctuate from one to the other right at the quantum critical point. It costs a little bit energy if you're to the side of it, but you can afford that little bit of energy over a short amount of time. That's Heisenberg's uncertainty principle. Delta E times delta T can never be smaller than h bar. So that means you can, given that there's only a small difference in energy between the two states, you can have some finite time over which a patch can fluctuate to the opposite state.
Okay. Yeah, I think that helps give a bit more intuition.
Okay.
I wasn't really familiar with this kind of terminology and stuff before.
Yeah. I appreciate that, but if I don't know which direction you're going to go off, but quantum criticality is something which is actually discussed quite widespread throughout condensed matter and actually also beyond in atomic gases and it probably even has some it has links to things like relativity theory through this anti-de Sitter conformal field theory.
Okay, thanks for that.
Any other questions?
Hello, Sven.
Sure.
Yeah. So you said that in the quantum critical regime, so if you are in the quantum critical regime, the thermal fluctuations is higher than the quantum fluctuations, and if you cool down the system, it doesn't know in which order it'll be. Why is that?
If the the thermal fluctuations are larger than the energy difference between the ordered and disordered state, it means that there's more fluctuations, more thermal fluctuations happening than the inclination to go into one or the other state. And that means you can't actually tell. If something is noisy, essentially, you can't tell if the noise is larger than the signal, you can't tell that there's a signal. And that's essentially similar here, that the system can't tell where it's going to end up as long as it's fluctuating with a thermal energy that's much larger than the quantum energy. It will, of course, tell if you keep on cooling down, because KBT is getting smaller and smaller as you go vertically down here. And at some point, you'll leave that regime. KBT is going to become smaller than the difference, and that's when the system really will know. But what I want to say mainly is that this makes this whole regime one unique regime, where it doesn't matter whether you're here or there, because thermal fluctuations are larger than the difference, and hence the system won't know where it's really going to end up, and hence the system is going to behave the same over here like it is over here. And that's what we've indeed seen on this picture of ytterbium rhodium 2 silicon 2. The resistance is linear here and here because it simply doesn't know whether it's going to end up on the Fermi liquid or on the antiferromagnetic side. Then the resistance exponent starts to cross over, because this is not a sharp boundary, but it's a crossover. It crosses over to the T² behavior inside the Fermi liquid behavior phase here, or region.
Okay. Are the quantum fluctuations basically the ones that are inducing the order then, and deciding whether it is going to be ordered or disordered? Because in the ordered state and the disordered state, that's where the quantum fluctuations are going to be higher than the thermal fluctuations. So are we saying that the quantum fluctuations are the ones that are inducing the order or disorder between the...
Maybe I wouldn't call it that, because what's the ground state is dictated by the interactions, and you can picture that as a Hamiltonian, of course, which tells you what is the lowest energy state. And at zero temperature, you will get that lowest energy state, because we're talking here, we're talking always about equilibrium here. So the quantum fluctuations can get you from one state to the other, and they will help you to make sure that you always end up in the ground state, just as the thermal fluctuations do. So if you, for instance, start your material in the quantum ordered state, and then you increase pressure to make it more likely to become disordered, then the quantum fluctuations are going to help you to get from one to the other, because it'll start fluctuating. Larger and larger patches will turn into the opposite magnetization, and eventually you'll have even number of both patches, and those fluctuations die out as you go here. So that means way over here you'll have a static picture of even number of positive and negative magnetization in the case of a ferromagnet, but they won't be fluctuating anymore because the cost of flipping is large, because you're far away from the quantum critical point where the cost of flipping is 0. Similarly, as you cool down, here the flipping is done, or if we go down this route, the flipping is done as induced by the thermal fluctuations. Vice versa, we can of course start at low temperatures again and go up, and the melting of the order is started by thermal fluctuations, because they can be, they will be large enough in energy to actually pay that energy that it requires to flip some patches. And that's when we then end up here at high temperatures with a dynamic disordered state where all the patches continue to flip, but on average are always even number of positive and negative magnetization, but it's a dynamic state up here compared to a more static state the further you go to the away from the quantum critical point over here.
Oh, okay. I think that one last question. I think I still don't really see the difference between the Kondo effect and RKKY interaction, because both involve the local moments, F electrons within the lattice, and I mean they interact with the conduction electrons. But I mean I can see, I mean the main difference is that in the Kondo effect, I guess the local moments are just oscillating between up and down spins, and the average is just going to be 0. And the conduction electrons are, I guess, scattering off the local moments. But what is the difference between these two? I mean, they sort of seem to originate from the same thing, I guess.
That's true. They originate from the same interaction, namely this exchange interaction, which here is included as J, and which of course also features inside there. In this I, we will also have a function of the distance. So last time we've had this cosine 2kf times r divided by r to the 3. That will all be in there. But the most important bit is that the Kondo effect is an interaction between the local moment and the surrounding conduction electrons. The RKKY interaction is actually an interaction between two local moments, which is mediated by the conduction electrons. So the conduction electrons, of course, mediate what's going to happen if you've got two local moments that sit at a certain distance apart, and at short distances, it will give you a ferromagnetic alignment, then antiferromagnetic, ferromagnetic, and so on. And that will mean the sign of this interaction I is going to flip. But the important bit is that it wants to give you some magnetic ordered state where the local moments are going to be ordered either ferromagnetically or antiferromagnetically. Yes, it originates both from the same ingredients, but it's different processes. This involves scattering. This does not involve scattering. It's actually the RKKY interaction. Actually, all it requires is the Pauli exclusion principle. Local moments and conduction electrons, don't want to be of the same state. Of course, there's I mean, on a fundamental level, it's all electrons and they are indistinguishable. So you can't really make the distinction between conduction electron. You can't pin a label to an individual electron and say it's now in a conduction state and now it's in a local state. They can, of course, swap. And that is exactly what's happening when exchange is happening. So in that sense, essentially, you need this to happen twice, namely with one local moment at the origin, conduction electron, and then the local moment wherever the next one is. So in that sense, I can see where your confusion comes from. As often the case, the Kondo and RKKY Hamiltonian are derived as different limiting cases of the interactions happening, and we've made the we've essentially condensed this interaction between two local moments in this effective exchange interaction Ij here, whereas in the case of just one scattering, it's all in this exchange interaction J here. So both are happening on top of each other, and they are of course originating from the same electrons, conduction and local moments. I can see why that causes confusion, but there are certainly similar examples elsewhere in physics where you've got the same ingredients giving rise to different interactions. So say even two electrons, you've got Coulomb repulsion and gravitation happening. Of course, gravitation between two electrons is nothing compared to Coulomb interaction, but you can see that they can still give rise to the same to two different interactions. And similarly, that's the case here.
All right, I get it, understand, I think. Thanks.
Okay, any more questions? If not, then I'll close the session here. And as I said, it's 5 lectures that I wanted to get through, and I think we're probably good off to leave it here. And I expect that you'll be picking up some of those concepts when you start the many-body lectures with Stephen Clark. I expect that he will approach it much more from a theoretical point of view. If you've got any more questions, please feel free to come back to me. I made the offer of setting some problems. Do you want to tell me now if you would like to do that, or do you think
Yes, please.
Okay, then I'll email out. Paul, did you want to make a statement?
I'm sorry. Yeah, I was just going to say. Yeah, I would quite like to look at some problems. I can't be 100% sure I have time to actually complete them or not. But I would like to have a look if that's okay. And if I can manage, I will.
I will prepare them in the next days and send them out via email. Or actually, I'll send them to Tom, and he can forward them to all of you.
Great. Thanks. Thanks for all of this.
Okay, good. So then I'll stop sharing my screen, and I'll close the session for today. And yeah, do feel free to contact me via email if you've got any more questions.
Okay, thanks again. Bye.
Thank you. Bye-bye.